So hello and welcome to today's lesson. So today's lesson is going to be on the residue theorem, and it's a continuation of our study of complex analysis. So basically, in this video we are going to go through how to find the residue of a complex valued function. Okay, so we have various rules that we have to know to be able to find the residue. You'll be going through all the rules with a lot of examples to make sure that you really get the understanding. So let's start by defining what the residue means. Okay, so suppose z naught is an isolated singularity of f of z, and it has Lorentz series given by what we have here. Then we define the residue of f of z at z naught to be the coefficient this of what we have here in the Lorentz expansion. Okay, so I'm going to expand this for you to know the residue that I'm talking about. Okay, so when we take some expansions of this Lorentz series that we have here, we are going to have this. And if you followed our last video, you could see this is very similar. Okay, where we said this is the analytic part and this is the principal part. So the analytic part has positive powers and that of the principal part has negative powers. Okay, so you can see that when it comes here, we have a minus 1 times 1 over z minus z naught. Okay, so this happens to be the coefficient of that. So that means that this here is what we term as the residue of our expansion here. Okay, so always that's what the residue is. So you can go through the definition again. I think it's very simple to comprehend. So now we know that that's the residue. So that means that whenever you are being given a function f of z, you can find the Lorentz expansion and you can find for that coefficient of the first principal part. And that's going to be the residue. But sometimes it's very difficult to get the Lorentz expansion. Okay, so we have rules, and the rules helps us to be able to find the residue in a very quick way. And that's the reason why we will be going through them. So rules to find the residue of a complex function. So we have the first rule. So the first rule is very simple from the definition. So it says that you have to compute the Lorentz expansion of f of z around z naught in a coefficient of the term 1 over z minus z naught, which is this, becomes the residue of the function at z naught. And I hope with this is from the definition of what a residue is, so we all understand that. So let's solve one example, okay, and you will get what we are saying. So this one says find the residue of sine z over z squared. Okay, so we are coming to find the Lorentz expansion of what we have here. So note that the Taylor expansion for sine z is given by what we can see here. Okay, so if you don't know how this expansion is done, then after this video you can go to the internet and search for the Taylor series for sine z. Okay, and you'll find out there with a detailed explanation. So this explanation I can give to you is that the Taylor series for sine z is given by this power series here. So when you expand this and you collect some terms, then you can have these ones here. So let me do this z, because this time around we're talking about sine z and not z. Right, so I hope you guys get it. Okay, then let's continue. So you should know that sine z alone is what we have here. So now we had sine z over z squared. So that means that this is 1 over z squared and this is the sine z. So now we can multiply 1 over z squared through. When we do that, we are going to get what we have here. So z over z squared, z cube over this over this, and that over that, continuing, right? So here, we have twice of the z's here. So one can cancel this and you'll be left with 1 over z. And this also continues. So you could see that 1. So 1 here, so this can be written as 1 times 1 over z minus 0, right? So you could see that this one here happens to be the coefficient of what we have here, or that's the coefficient of the first principal part. So meaning the residue of sine z over z squared at 0 is 1. So from the first rule, that's how we can find for the residue of a complex function. Okay, so we first find for the Laurent expansion, then the coefficient of 1 over z minus z naught becomes the residue. So now let's go to the second rule. So the second rule says that if f of z has a simple pole, and by now you should know what a simple pole is, right? So a simple pole is a pole of order 1. So in our previous video we talked about that at z naught. Then the residue of f of z comma z naught is equal to the limit as z approaches z naught of z minus z naught times the function f of z. So I want you to take note of the second rule. So it is also very simple to apply that to solve questions. Actually, as we solve questions, you will really understand the second rule as well. So this question says find the residue of f of z, and we have f of z to be cos z over z raised to the power 4 minus 1 at z naught equals I. So the first thing that we have to check is whether I here has a simple pole or not. Okay, so before we can do that, then we have to expand the denominator of f of z. So expanding the denominator of f of z will give us what we have here, and this can further be broken down to what we have here. So that means that f of z can be written as cos z, in the denominator we can have this. So you could see that here when it comes here, we have 3 singular points. No, we even have more than 3. Okay, we have 4 singular points, that is plus or minus I and plus or minus 1. But when it comes to our I, the one that the question gave us, you could see that we can find it here, because when z is I, this part goes to 0. So you could see that here it is a pool of order 1 because you have raised to the power 1 here. So that means that the z naught is a pool of order 1. It's a simple pool, so we can use the root 2 for it. So that's what I've written here, that it is obvious that f of z has a simple pool at z naught equals I. So we can use root 2. So root 2 says that the residue of the question will be equal to, so the limit as z approaches z naught, in this case z naught is I, then z minus z naught, in this case it is I, times the function. So you can see that here this cancels that, so we'll be left with this. Okay, then the next thing is to put in our limit of, is to put in our limit. So putting our limit is going to give us cos I, then I squared minus 1, then times I plus I. Okay, so here we should know that I squared is the same as negative 1, and I plus I will give us 2I. So that's what we have here. Then here we have I squared minus 1, but I squared is negative 1, so negative 1 times negative 1, negative 1 minus negative 1, then all times 2i. So this will give us what we have here. And finally we end up with cos I over negative 4i. But when you get here, you can decide to rationalize. So we have negative cos I over 4i. You can decide to multiply it through by 4i, also divide through by 4i. So you can leave it in this form, or you can further simplify it to what I'm showing here. So you could see here, you're going to get 4i cos I. Okay, we have a negative sign here, and this will give us 16i squared, right? But I squared is negative 1, so that means you're going to get negative 4i cos I over negative 16, which will give us I cos I over 4. So yeah, I think that's correct. Okay, so that's using the second rule. Okay, using the second rule. Then let's go to the third rule. So don't worry, at the end of this video I'm going to give questions where the questions won't be under any of the rule. Then we will know how to know whether we have to use rule 1 or rule 2 to solve it. Okay. So the third rule says that if f of z has a pool of order k at z0, then the residue of what we can see here is equal to 1 over m minus 1 factorial. Then the limit as z approaches z0, then the derivative of the power m minus 1 of whatever we can see here. So take note of this. Okay, so where m is greater than or equal to k, but in most cases m is equal to k. So let's take an example. Okay, so you could see that here the question says we should find the residue of f of z equals whatever we have here at this point, pi. So you could see here our pool is pi, but pi has an order of what, 3, which is not a simple pool, because for it to be a simple pool, then it has to have an order of 1. So that means we can't use root 2, okay, because the pool is of order 3 and not 1. So that means we can use this third rule, okay, because the pool has an order of 3. It's a triple pool. So let's solve it. So f of z has a pool at, and the order of the pool is 3, so hence m is 3, right? So using the equation in root 3, so we are using this particular equation. Then the residue of what we have here, this is in the question, is equal to 1 over, you should know we're having m here, but here our m is 3, so we do that replacement. Then wherever we find our m, we put 3 there. Wherever we find our z0, we put pi there in the question. Okay, so you could see that here this will cancel this. Then this will give us 1 over 2 factorial. Then the limit as z approaches pi, then d squared is z squared of this function that we have here. So that means we have to differentiate these 2 times. Okay, so let's do that differentiation. So when we differentiate this once, z cos z, we get this. And when we differentiate it for the second time, we are going to get what we can see here. Okay, so the first derivative gives us this and the second gives us this. So the next thing is we can now put them inside our formula. So now this is the derivative that we found, so we have this there. So, and 2 factorial is the same as 2, so 1 over 2 times whatever we have here. So as z approaches pi, when you put it inside, then we have this. Okay, but you should know that pi rad in degrees is like 1 180 degrees. Okay, so when you evaluate 2 sine pi, you're going to get 0. Then cos pi will give us -1. So when we simplify it, we are going to get plus pi, right? So whatever we have here will give us pi. And when you multiply it through, you're going to get pi on 2. Okay, so this happens to be the answer for that particular question. Okay, so let's move on to the fourth rule. So the fourth rule says if f of z and g of z are analytic at z0 and g of z has a simple 0, at z0, then the residue of what we can see here is equal to this, right? So you could see that it is f of z0, then g prime of z0. So that means you're going to find the first derivative of our function g of z. So f of z are analytic at z0 and g of z has a simple 0. Okay, it always has a simple 0. So we have this question here. We say if you should find the residue of z cubed z squared plus 1 at z0 is equal to I. Okay, so we can let this be f of z and this be g of z. And you could see that when you put this I here, you're going to get I squared plus 1, which will give us -1 plus 1, 0. So that means that it has a simple 0. Okay, so then we can use rule 4. So using rule 4, the residue of z cubed over z squared plus 1 at I, when you use the rule 4, you're going to find to be f of z0 over j prime of z0. Okay, so when you make substitution, you're going to get I cube here because we have z cube here, so I cube. Then when you differentiate z squared plus 1, you're going to get 2z. So when you put in the I, then you get 2i. So this is going to give us I cube over 2i. The I can cancel one of the 3 i's for the numerator. And we get I squared over 2. And note that I squared is the same as -1. So this gives us -1 over 2. So that's it for the rule 4. Okay. Then the rule 5. So it says, actually the rule 5 is just like a case, one case of the rule 4. So it says, if g of z is analytic and has a simple 0 as z0, then the residue of 1 over g of z. So you could see with the fourth rule we had f of z here, but here we have 1. So it's just like one of the cases of the fourth rule. So this is given by what we have here. So j prime of z0. Okay. So let's get an example. So you could see this is the same example, but just that the numerator we have 1 as z0. So we just go through the same thing. So we have 1 over z squared, then comma I. So this will be 1 over, when you differentiate this, you get 2z. Then when you put your I inside, you get 1 over 2i. And when you get this, you can decide to rationalize and you get 1 over 2i times 2i over 2i. And this will give you 2i over 4i squared, which will give you 2i over -4, which will give you -I over 2. So we are done with the 5 rules, okay? But I want us to solve more examples because I know someone will ask, okay, so when a question is given to me, how will I know that I have to use rule 1, rule 2, rule 3, rule 4, rule 5? So let's solve these 3 examples, and by the time we are done, your question would have been answered, okay? So it says, evaluate the following residues. So you have to find the residue here, that, and this. Okay, so let's solve it. So you could see that here 0 is our pool, because when you put 0 here, f of z is going to be undefined, but it has an order of 5, right? So you can see we can use the second rule, okay, right? So this is the second rule, the formula for it, and in this case our m is 5. So we are going to make substitution. Then we have this. So we have to differentiate. So this will cancel this. Then we have to differentiate ez 4 times. But you should know that for the exponential function, even if you differentiate it 1,000,000 times, it will still be the same thing. Okay, that's when you have ez. Okay, so even when you differentiate this 4 times, you'll still get ez here, and we have 1 over 4 factorial here. Then we put in 0. So when you put in 0, you get e0, which is the same as 1. So this will give us 1 over 4 factorial times 1. And 4 factorial is 24. So this equals 1 over 24. So you can see it's very, very simple. From the question, as long as you see the question and you know the rules, you'll be able to know which of them you're supposed to use. Okay. Then with the second question, we have 1 over z squared plus 4 at 2i. So you can see that with this you can use the rule 5. Okay, so with the rule 5, you just have to differentiate the denominator and put in your z0. In this case, our z0 is 2i. So this is it here. When you differentiate our j, we get 2z. Then when you put in the z0, which is 2i, then we have these, and multiplying this will give us 1 over 4i, which is same as negative I over 4. Okay, so I hope you understand the reason why. If you multiply it through, divide through by 4i, you're going to end up with this. So it's very, very simple. As soon as you see the question, trust me, if you know the rules, you'll be able to identify which of them you're supposed to use. So the last question, then we wrap up. Okay, so residue of cos z at 0. Okay, so yeah, this one you're going to apply a bit of trigonometry here. So we know that cos z is the same as 1 over tan z. So now, as soon as we put it in this form, then we can use, of course, the fifth rule, right? So we use rule 5, and you should know that with rule 5, it will be 1 over j prime of r z0, which is 0. So when you find the derivative of our g of z, that's tan z, you're going to get sec squared z. And sec squared z is the same as sec z all squared. And sec z is the same as 1 over cos z all squared. So when you put in the 0, then you get 1 over cos 0 all squared. But cos 0 is 1, so you're going to get 1 over 1 all squared. So this gives us 1 over 1 all squared, which is equal to 1. So you are going to get 1 over 1, which is the same as 1. So meaning the residue of cos z at 0 is 1. Okay, so yeah, thank you very much for following. And if you didn't get anything, you can go ahead and rewatch the video, and trust me, the understanding will come. Okay, so I'm going to can read a final year student of mathematics KNST, and thank you very much, and I wish you all the best.